And we're back. Hi, guys. In this lesson, we are going to learn about fiber optic cables, so we're going to get right to it. So, what are fiber optic cables? So, fiber optic cables are a type of cable, right? But you got to get this, the core part is made of glass, or sometimes plastic, where the light signal is sent, and the acrylic coating applied on the core, covered in the desired colors, and placed in loose and tight tubes, reinforced with glass fiber and Kevlar as a strength element, and containing a protective outer sheath. So yeah, fiber optic cables use light signals as opposed to electrical signals to send their data. Fiber optic is a type of cable similar to an electric cable, but containing one or more fiber optics used to carry light. So optical fiber elements are typically individually coated with plastic layers and contained in a protective tube suitable for the environment where the cable is going to be placed. It's suitable for indoor and outdoor use, as well as underground and overhead use between poles. So where are you going to see fiber optic cables actually used? Well, fiber optic cables are used in numerous applications involving voice, video, and data transmission. For example, it's used by commercial enterprises, governments, the military, and many other industries. In fact, here's some sample usage areas: closed-circuit television systems, data transmission, LAN and WAN and multimedia applications, connections between switchboards, connecting active network devices at high speeds, connecting devices at long distances, on billboards, in devices used in medicine, in places where nuclear power plants and radioactive beams disrupt communication, in low-speed applications where electrical noise is high, also in applications that require point-to-point security. Fiber optic cables can be attached to communication equipment and patch panels to provide a physical connection to a network or device. So how would you design a fiber optic cable? Well, fiber optic cables consist of a core selected for internal reflection and a coating layer. The coating layer is usually covered with a layer of acrylic. This coating protects the fiber core from damage and allows for easy fiber selection when there are multiple fibers in the same tube. But this acrylic dye does not add to the optical waveguide properties. Individually coated fibers are placed in a tight or loose tube. These tubes can be turned into a single tube or multi-tube cable as needed. In multi-tube cables, the tubes are twisted in the S and Z directions around the central member to form the cable core. Kevlar or glass fiber is used to provide the desired tension on the cable core. However, it can be single-sheathed or multi-sheathed, as well as metal-containing armor or metal-free armored options. And as a last layer, it is covered with a special outer sheath material and converted into a cable. For indoor applications, the fiber is usually coated with a flexible and strong strength member such as Kevlar to form a simple cable. Each end of the cable is terminated with a special fiber optic connector for easy connection. For use in more demanding environments, a much more robust cable structure is required. The fiber is enclosed in semi-tight tubes that allow it to be stretched without straining it. This protects the fiber from stress when it's installed and due to temperature changes. Fiber tubes can be a gel-free tight tube or a gel-filled loose tube. A critical issue in outdoor cabling is to prevent water contamination of the fiber. This is achieved through the use of solid barriers such as copper tubes and water-repellent gel or water-absorbing powder surrounding the fiber. Fiber core dimensions. Fiber properties show core and cladding diameters as a ratio. Multimode fiber is usually used at 62.5 to 125 or 50 to 125 microns. Single-mode fiber as 9 to 125 microns. Fiber optic core types. There are two types of fiber optic cables used today: multi-mode and single-mode. Multi-mode fiber optic cables have an outer diameter of 125 micrometers and a core diameter of around 50 micrometers. And the traveling light travels through multiple paths. Receiving and sending data is slower and shorter distance than single-mode fiber optic cable. Single-mode fiber optic cables, on the other hand, are reduced to less than 10 micrometers in diameter to allow only one type of propagation, and all of the traveling light travels in a single path. They transmit high-capacity information better than multi-mode fiber because the signal has no propagation and no propagation by hitting the coating. Multi-mode fiber optic. They have a core diameter of about 50 microns and 62.5 microns. They transmit infrared laser light with a wavelength between 850 and 1300 nanometers as the optimum value. It is the most used cable type because its production cost is more affordable. The amount of loss is higher than single-mode cables. Multi-mode fiber optic cable is generally preferred in a local area network for data transmission. Multi-mode fiber optic cables do not require high-sensitivity connectors, as the large core diameter allows for a large margin of error. In this way, more economical connectors, parts, and active elements are used compared to single-mode cable. Inexpensive LEDs are used for light transfer and sensing in multi-mode cables. Multi-mode fiber optic cables are produced in two forms: 62.5, 125, and 250 micron core diameter, sheath diameter, coating diameter, and 50, 125, 250 microns core diameter, sheath diameter, and coating diameter, according to the core diameters. Multi-mode fiber optic cables are divided into two groups according to their index structure. 1. Step index multi-mode fiber. A multi-mode fiber arrangement with a step index is similar to a single-mode fiber arrangement. The difference is that the central core is much wider. Bandwidth of step index multi-mode fiber is 10 to 50 megahertz per kilometer or more. This type of fiber has a larger light fiber opening, thus allowing more light to enter the cable. Light rays striking the boundary between the core and the protective envelope at an angle greater than the critical angle propagate in a zigzag pattern in the core and are constantly reflected from the boundary. Light rays striking the core protective envelope boundary at an angle less than the critical angle enter the protective envelope and disappear. It can be seen that there are multiple paths that a light beam can follow when propagating in the fiber. As a result, not all light rays follow the same path, so they do not travel the distance from one end to the other in the same amount of time. 2. Graded index multimode fiber. The graded index of the core and the structure of the multimode fiber varies depending on the radius. That is, when viewed from the outside with very sensitive and powerful microscopes, it is in concentric rings from the inside out. Each of these rings has a different index of refraction, and the index of refraction decreases as you go from the inside out. In other words, the largest index in the center and the smallest index in the outermost. The number of these layers varies according to the manufacturer. Usually, the number of these layers is between 50 and 400. Light that goes directly at the center travels little. However, here the index is large. In the outer layers, the distance traveled by the outgoing light is greater. However, since the index is small in these layers, the speed of light varies inversely with the index appearance. Therefore, all lights converge at certain nodal points. There is a delay between pulses at the receiving end. However, the latency step index is less than that of multimode fibers. In this type of fiber, the bandwidth ranges from 200 to 300 megahertz per kilometer to 5 to 6 gigahertz per kilometer. Multimode fiber optic advantages and disadvantages. During fiber optic termination application, thanks to the larger core diameter, fiber ends are more easily aligned, providing shorter termination, is one of the multimode fiber optic advantages. Due to its limited speeds, it is limited, especially in large-sized applications, which is a multimode fiber optic disadvantage. The connectors, components, and active elements used are more economical than single-mode cables, which is an advantage of multimode fiber optics. Cable prices are more expensive than single-mode cables, approximately by 2 times, which could be considered a disadvantage. Cheaper LEDs are used for light transfer and sensing, which is another advantage of multimode fiber optics. Access distances are very short compared to single-mode cables, which would be considered a disadvantage of multimode fiber. Types of multimode fiber optic cables. Multimode fibers were originally produced in various sizes for use in a variety of sources. But the data industry, 62.5 to 125 fiber, which was standardized in the mid-1980s at 62.5 core fiber, had a 62.5 micron core and a 125 micron cladding. Recently, an old fiber design was revived when gigabyte and over 10 gigabyte networks became widely used. 5125 fiber. Lasers were used for radio applications from the late 70s before single-mode fibers were available. 5125 fiber, OM2 standard, offers higher bandwidth with laser sources used in local networks and can allow gigabyte links to travel longer distances. Today, the newer OM3 or laser-optimized 5125 fiber is considered the best choice for multimode applications. OM4 fiber provides higher bandwidth for 10G plus networks. OM5 is broadband multimode fiber optimized for wavelength division replication with VC cell in the 850 to 950 nanometer range. Types include OM1, orange color, core size to 62.5 microns, data rate 1 gig at 850 nanometers, distance up to 300 meters, applications, short path networks, local area networks, and private networks. 62.5 125 multimode fiber cable. OM2, orange color, core size 50 microns, data rate 1 gig at 850 nanometers, distance up to 600 meters, often used for shorter distances. 2 times the range capability of OM1. Applications include short path networks, local area networks, and private networks. OM2 fiber optic multimode cable. OM3 laser optimized multimode. Color is turquoise. Core size 50 micron. Data rate 10 gigs at 850 nanometers. Distance up to 300 meters. Uses less speed mode. Provides increased speeds. Can run 40 gigabytes or 100 gigabytes up to 100 meters using MPO connectors. Applications: larger private networks. 10 gigabit laser optimized OM3 fiber optic cables. OM4 laser-optimized multimode. Color, violet. Core size, 50 microns. Data rate, 10 gigabytes at 850 nanometers. Distance, up to 550 meters. Ability to run 100 meters up to 150 gigabytes using MPO connectors. Applications, high-speed networks, data centers, financial centers, and enterprise campuses. OM4 50-micron multimode 10 giga 550-meter optimized cables. What is OM5? According to ISO IEC 11801, OM5 fiber defines a wider wavelength range from 850 nanometers to 953 nanometers. It was created to support short wavelength divisional replication, or SWDM, one of the many new technologies developed for 40 gigabit per second and 100 gigabit per second transmission. In June of 2016, ANSI TIA 492 AAAE, the new broadband multimode fiber standard, was approved for publication. And in October 2016, OM5 fiber was officially announced by the ISO IEC 11801 for cabling with WMMF, or broadband multimode fiber. From now on, OM5 could be a potential new option for data centers that require larger link distances. Single-mode fiber. They are thin, centered cables with a diameter of approximately 9 microns and transmit infrared laser light with a wavelength between 1300 and 1550 nanometers. Since this cable core has a very small diameter of 9 microns, there is only one path that light can follow as it propagates in the cable. There is only one light direction in the fiber that travels at a very specific wavelength. Therefore, all light rays follow approximately the same path in the cable and travel the distance from one end of the cable to the other in approximately the same time. This is one of the most important advantages of single-mode cables. In addition, since there is only one light option in this cable type, there is no emission. This provides less propagation loss and more information carrying capacity. Single-mode fiber optic advantages and disadvantages. It can be used in very large systems reaching distances up to 100 kilometers without any problems, is only one of the advantages of single-mode fiber optics. Due to the smaller core diameter, the fiber termination application becomes more laborious and long-lasting, which could be considered a disadvantage of single-mode fiber optics. It supports high bandwidths and high speeds, up to 10 gigabits per second, which is definitely an advantage of single-mode fiber optic cable. Due to its small core diameter, it needs perfect connectors, so connector and pigtail prices are very expensive, which could be a disadvantage of single-mode fiber optics. The price of single-mode fiber cable is 2 times cheaper than multi-mode cable, definitely an advantage when considering single-mode fiber optics. But much more expensive laser diodes are used in communication than just LEDs, which is a disadvantage of single-mode fiber optics. It is the only type of fiber optic cable used in long-distance connections because of its very good performance, a superior advantage of single-mode fiber optics. Yet single-mode fiber components, converter devices, and active products are very expensive, which is among one of the higher disadvantages of single-mode fiber optics. Fiber optic cable coating materials. The coating material is application-specific. The material is resistant to UV radiation, oil, and other chemical resistance. It determines the mechanical strength caused by the reasons. Today, PVC is predominantly replaced by halogen-free alternatives due to stricter regulations. LSFH polymer is halogen-free, but its UV resistance is weak. Therefore, it's good for indoor use. Polyethylene, or PE, is halogen-free. It's got good UV resistance, so that makes it good for outdoor use. Polyurethane, or PUR, is halogen-free, displays good UV resistance, and makes highly flexible cables. PBT is halogen-free. It displays medium UV resistance, and that makes it good for indoor use. PA is also halogen-free. It's good in UV resistance, and that makes it good for both indoor and outdoor use. Fiber optic color codes. Fiber optic cables used indoors and outdoors are usually color-coded to indicate the fiber type used. Strain relief booting, which prevents fiber bending in a connector, is color-coded to indicate the type of connection. A plastic sheath connector, such as an SC connector, typically uses a color-coded sheath. The standard color codes for jackets or bumpers and boots or connector covers are orange for multimode fiber optic, turquoise for OM3 or OM4 10G laser optimized 5125 micron multimode fiber optic, violet OM4 multimode fiber optic, and yellow single mode optical fiber. A few commonly used fiber connectors include ST with a connection type that twists on. Fiber type is used single mode and multimode. With a ferrule type of PC and UPC, fiber count of 1, typical applications LAN, interpretation with switch. Connector type FC, connection type screw. Fiber type single mode multimode. Ferrule type PC, UPC, APC. Fiber count 1. Typical applications datacom, telecoms, and other communications. Interpretation with switch. Connection type SC. Click fit. Fiber type single mode multimode. Ferrule type PC, UPC, APC. Fiber count 1. Typical applications include CATV and test equipment. Interpretation with switch. Connector type LC. The connection type click fit RJ45 style. Fiber type single mode multimode. Ferrule type PC, UPC, APC. Fiber count 1. Typical applications Gigabit Ethernet, video, multimedia. Interpretation SFF or small form factor. Connector type MU. Connection type push-pull. Fiber type single mode multimode. Ferrule type PC, UPC, APC. Fiber count 1. Typical applications medical, military. Interpretation SFF, small form factor. Connector type MT-RJ. Connection type click fit RJ45 style. Fiber type single mode multimode. Ferrule type not available. Fiber count 2. Typical applications Gigabit Ethernet, asynchronous transmission mode or ATM. Interpretation alignment. One must have mating connectors. Connector type MPO MTP. Connection type push-pull. Fiber type single mode multimode. Ferrule type NA. Fiber count 4, 8, 12, 16, 24. Typical applications Active device transceiver, connections for OE modules. Interpretation, alignment, one must have mating connectors. Well, and that is it. We're done with this lesson. We learned a lot about fiber optics, what they are, what their design is, single and multimode fiber optic cables, and the commonly used fiber connectors. I hope you learned a lot. Well, a lot of useful information anyway. See you in the next lesson.